Hello, welcome to the probability course. I am Jyotishman Chatterjee. This course is intended for people who need probability to apply in certain disciplines like engineering or data science or finance, etc. So in order to apply, they need basic knowledge about the topic of probability, and that's the purpose of this class. So let's start. And in order to do that, let me bring out the PPT. Here it is. Introduction to probability. What's the basic goal of this discipline? Any discipline, say geology, talks about earth, what's there inside, etc., etc. Chemistry talks about chemical things, reaction, and other stuff like that. Zoology talks about animal kingdom. So what's the goal of this topic of probability? It tries to measure chances. That's what it does in a nutshell. In order to understand that, let's first talk about different kinds of statements. Some statements are universal truth. Say, for example, the earth moves around the sun. It's always true. An universal truth. Similarly, Monday will follow Sunday. That's another universal truth. That always happens. Although it's our convention, what's Monday and what is Sunday, but once that is defined, Monday will always follow Sunday. Let's look into the other extreme. There are statements which are never true or absurdity. Say, for example, horses lay eggs, or throw of a die will produce 7. We know that a die has 6 faces, 1, 2, up to 6. So whenever we roll a die, it will produce either 1 or 2 or up to 6, but it can never yield 7. So both the statements are absurdity. In other words, will never happen. Now there are some in-between things. The things that may be true or may not be true depending on circumstances. What are those? Let's talk about a few. Suppose my statement is getting a cloudy weather tomorrow. So it may be true or may not be true depending on how is the weather tomorrow. Another statement, roll of a die producing an odd number. We know that a die produces either 1, 2, 3, 4, 5, or 6. However, sometimes the outcome will be one of the 3 numbers, 1, 3, or 5, in which case it's odd. And some other times it will produce 2, 4, or 6, which is even. So this statement, that roll of a die producing an odd number, it's sometimes true and sometimes not. Similar statements are a man surviving 80 years. That depends on which man we pick up. Some people do survive 80 years and more, and many don't. So again, it's neither universal truth nor an absurdity, but somewhere in between. So is passing an exam, because some people will pass and some people will fail. So it depends on the particular person and the particular exam that we are talking about to decide whether that particular person has passed that particular examination. So is winning a battle. One may either win or lose, or getting a bus within 5 minutes. Say you are waiting at the bus stop for your bus. You might get the bus within the next 5 minutes, or you might not. So, intuition of chances. After having talked about the statements which are sometimes true and sometimes not, natural question is, what is the chance of such statements being true or such events holding? What's the chance of such events holding? Probability talks about how to calculate such things. That's the detailed way or scientific way of handling it. But even without calculation, we have some fairly good idea about comparing chances of different events. Let's get into some examples. The jet engines or aeroplanes before the year 1958 used to have 4 jet engines in the plane. One purpose of that was, of course, to have more power, which gives its more capability to airlift the weight. Along with that, another purpose that it served was building redundancy, meaning even if 1 or 2 jets or 1 or 2 jet engines fail during the flight, still it will be able to reach the destination with the remaining functioning ones. So it increases reliability. Of course, with time, things have improved, and these days, most of the jetliners have only 2 engines, and those engines are a lot more reliable compared to the earlier ones. So it's quite safe to have 2 engines these days. So even if one goes down for some reason, then the other is capable of carrying the passengers to safety. So in a nutshell, adding more engines, what it does is it increases the reliability or reduces the chance of accident. That's quite clear even without any calculation. How much chance will be reduced? That's a more detailed calculation. But even without calculation, we can say that if we add more engines, then there will be less chance of accident. Now let's take the example of life insurance premium. We know that the insurance premium increases with age. Why is it so? Let's compare 2 persons. One person is 25 years old, another person is 60 years old. Now, suppose both of them want to buy 10-year-long life insurance for the same sum assured. Now, for the 25-year-old person, it's intuitively quite clear that the person's chance of death in the next 10 years is a lot less compared to the person who is 60 years old. So, insurance premium for the 25-year-old person will be a lot less compared to the 60-year-old person. Optimizing chance of getting a bus seat. Let's examine this example also. Let me build up the scenario first. Imagine you have just boarded a bus, and the bus has got 2x2 seats, quite a few. When you get into the bus, there are not many passengers who are standing. you are one of the standing passengers. Now you have got option of standing in front of a few seats. So it's up to you where you want to stand. And you know that within the next few minutes, the bus will get quite crowded. So you won't be able to move from one position to another. So with this expectation, you want to maximize your chance of getting a seat later on. Of course, you don't know who will be getting down where. However, you observe two seats. In one seat, you see there are two passengers who are amiably talking to each other, and the chances are they're traveling together, and also they will be getting down together. On another seat, where you may stand, you observe that the two persons are not at all talking to each other, and most likely they are traveling independently, separately. So they may separately get down anywhere. Whereas in the other seat, both the persons will be getting down together. So what I will do under these circumstances, I will prefer to stand in front of that seat where two persons are independent. Because if any of them gets down, I will be able to sit there. So the condition of my getting a seat will happen if one of the two events happen. Those two events are any of those two persons getting down. Whereas if I stand in front of that seat where two persons are traveling together, if they happen to get down, then I'll be getting that seat. So I am primarily banking on only one event. So this intuition plays a role for my decision. And again, here I don't need any calculation to convince myself which one is better or which one gives me higher chance of getting a seat. Now, this kind of mental calculation without really doing any numerical calculation actually takes place throughout the animal kingdom. Say predators, lions, tigers, they try to optimize their chance of getting a prey or hunting by remaining at the places where the prey will be visiting with higher chance. Say, for example, waterhole or grazing land, etc. And also say, you must have heard about great African migration, where lots of animals migrate thousands of miles. And why do they do so? Because they know where they are going, there is higher chance of getting food compared to where they are now. So there are a lot of this kind of intuitive game that plays on, not only among human beings, but also among other animals. Now let's slowly get into the formal framework of dealing with probability. First such thing is random experiment. What's a random experiment? It's an experiment whose outcome is not known until the experiment is performed. Typically, when we do other experiments like physical experiment or say chemical one, we typically know what is the outcome likely to be, and then we repeat that. And each time we repeat it, we get the same outcome. Now, compare that thing with random experiment. Here, the experiment is performed, but we don't know the outcome until the experiment is finished. Some examples. Suppose I roll a die. The die will produce either 1, 2, 3, 4, 5, or 6. But until the die stops rolling, I don't know exactly what's the outcome. This is a typical random experiment. another toss of a coin. So we know that the outcome will be either head or tail, but don't know the exact outcome until the coin lands up on the ground. Lifespan of an equipment, say you use an electric bulb, and how long that will survive, that will vary from one electric bulb to another. So again, it's a random experiment whose outcome is not certain until the equipment, here electric bulb, goes out of function, goes wrong. Another example, the number of days to recover from malaria. That will depend on the patient, and even for the same patient, it will depend on different instances. Say if the same person catches malaria a few times, the number of days to recover from malaria each time might not be different. Might not be same. So the number of days to recover from malaria is again a random experiment. Marks in a paper. Of course, it will depend on which person and which paper we are talking about. So it's again a random experiment, and the value of that thing will be done once the result is out. Now comes sample space. Say random experiment, the basic thing is we don't know the exact outcome until the experiment is performed. However, we know the set of possible outcomes of the random experiment. Say, for example, if we are rolling a die, we know the set of possible outcomes. It will be either 1 or 2 or 3 or up to 6. So this set of possible outcomes has a technical term. It's called sample space. Typically, we use the letter S or the Greek letter omega to indicate a sample space. If we roll a die, what's the sample space? As I told you earlier, it's the set 1, 2, 3, 4, 5, and 6. This consists of all the possible outcomes. So this is the sample space. What happens if I toss a coin? In that case, sample space will be the set consisting of head and tail. So H and T. Lifespan of a machine. Say, if we are studying the lifespan of a machine or equipment, the outcome can be any number starting from 0, including 0. The equipment might be non-functional to begin with. In that case, it will be 0, or it can be anything, say 3.5 hours or 16 years. Of course, you will have to include all these things in the same unit, say either hours or say seconds or minutes. But once you decide the unit, then it can be any number starting from 0 up to infinity. So that's why lifespan of the machine is lifespan of a machine has got sample space equal to the interval 0 to infinity, with 0 having been included. Days to recover from malaria. Of course, the person will take at least 1 day because the person is suffering from malaria already. So the number of days required, it can be 1, 2, 3, 4, etc. We just don't know how long it might take. So just to be on the safe side, include all the non-negative integers, although many of those might be redundant. Say, for example, 25,000 for theoretical study it will be okay to include it, but practically it won't happen. So as we don't know, let's include all the non-negative integers here. Marks in a 100 marks paper, the person has appeared for the test, and the marks can be anything from 0 up to 100. So here the sample space is 0, 1, 2 up to 100. So to repeat, sample space is the set of all possible outcomes of a random experiment, and we have seen quite a few examples. Two more examples here. First one, suppose we toss a coin twice. In this case, the sample space will be, remember, sample space should consist of all possible outcomes. So first thing that you should keep in mind is how you represent the outcomes. Here, we are tossing a coin twice. So we may represent the outcome as what's the first outcome, and then writing what's the second toss outcome. So HT will mean that the first toss gave me head and the second toss gave me tail. So writing this way, our sample space will be HH or HT or TH or TT. If I roll a die twice, say first roll might be any number from 1 to 6. Again, the second roll may give any number from 1 to 6. I can combine them together, say separated by comma, I comma j, meaning I is the outcome of the first roll and j is the outcome of the second roll. In that case, our sample space becomes 1 comma 1 or 1 comma 2 dot 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 1 comma 6 and so on up to 6 comma 6. So how many elements are there in this sample space? There are 6 into 6, that is equal to 36 elements. By the way, every element of the sample space is called a sample point. We will be using this terminology also in different places. Now, instead of rolling one die twice, what happens if we roll 2 dice simultaneously? Actually, the sample space will be same. Just one thing we'll have to do as convention. Just designate one of the die. You may either imagine a color or some distinguishing mark. Just designate one of the dice as number 1 and another dice as number 2. So when you roll both the dice together, what you will do is, suppose the outcome of the number 1 or the dice numbered 1 is I. Let me repeat. Suppose the outcome of the die numbered 1 is I, and the outcome of the die numbered 2 is J. In that case, you may write the outcome as I comma J. After having built this convention, you can write the sample space, that is the set of all possible outcomes, as I comma j, where I can be any number between 1 and 6, any integer between 1 and 6, and j is any integer between 1 and 6. So that way, this is same as the sample space that we talked about when we rolled a die twice. After having understood what is sample space, let's get into events. What is an event? It's a set of possible outcomes of a random experiment. We have already defined the set of all possible outcomes as the sample space. And what is event? Any set of possible outcomes is an event. So in other words, any subset of the sample space is an event. Now, events may either be described in terms of words, or we may designate the exact event by mentioning the subset. Say we are rolling a die. If we consider the event, the outcome is odd. When we say the outcome is odd, this is a specific event. What are the outcomes that are included here? The outcome can be either 1 or 3 or 5. So we are talking about this event, which is the set including the sample points 1, 3, and 5. So here our event is the set of 1, 3, and 5, which is same as the outcome is an odd number. Let's consider a few more events so that our understanding becomes clearer. Now let us consider the random experiment of tossing a coin thrice. Here the sample space is HHH, HHT, and so on up to TTT. There are altogether 8 sample points. That's what happens. When we toss a coin only once, we have got 2 sample points. Only H and T are the possible outcomes. When we toss a coin twice, we get 4 sample points. And when we toss a coin thrice, we get 8 sample points. So if we toss the coin 5 times, the number of sample points will be 2 to the power 5, that is equal to 32. Because each of the 5 tosses might give either head or tail. So altogether, we will be getting 32 possible outcomes. Now, if that is the random experiment, we can talk about the following events. So the first toss is head. This is an event. We have described it in words. What's the corresponding subset? First toss is head means the first one should be written as H. So the possible outcomes here are HHH, HHT. Let me write it down here. So HHH, here the notice that the first one is a H, or it can be HHT or HTH or HTT. All these 4 have the first toss yielding H. If our event is this one, third toss is tail, in that case, the corresponding subset will be HHT, HTT, THT, or TTT. This is the corresponding subset. Now comes another event, less heads than tails. How many this event? How many total tosses are there? There are 3 tosses. So either there will be 2 heads or there will be 2 tails, right? Or it can be all 3 heads or all 3 tails. So which all outcomes satisfy this? HTT, here only 1 head and 2 tails. So this satisfies less heads than tails. Similarly, THT, here also 2 tails and 1 head. So is this one. And triple T, here of course there is no head and 3 tails. So this also satisfies this condition. So for this event, less heads than tails, our corresponding subset is this one. How about the last but one? no head in first two tosses. No head in first two tosses. In that case, the first two tosses must give me tail. So here the subset is TTH and TTT. Let's consider another event. So this one, triple H, comma HTH, comma TTT. This is of course a subset. This is, I'm trying to mark this. This is a subset of the sample space. Here is the sample space. And as any subset is an event, so this is also an event. However, giving the description of this event might be difficult. That's what happens often. We may write some event mathematically as a subset of the sample space. However, giving the exact description in words might be difficult. Going the other way around is, of course, a lot easier in most of the situations. Say if you are given the description in words, then you can easily write down the subset by denoting the exact outcomes which should be included. Let me clear this. Okay. Now let me go to the next screen. Hold on a minute. Yeah. It takes a bit of time after using the pen to shift from one screen to another. So this is the events. These are the events that we talked about. And now let's come to the next question. When will we say that an event has occurred? We have understood what sample space, the set of all possible outcomes. We have also understood what is an event, any subset of sample space is an event. Now, when do we say that an event has occurred? An event A is said to have occurred if the outcome of the random experiment satisfies the event. Let's see an example. Suppose our random experiment is to throw a die. Let's consider two events. Event A is 1, 3, and 5. That is, the outcome is odd. And event B is only two outcomes, 1 and 5. Now, suppose we roll the die and observe that the outcome is 3. In that case, the event A has occurred because 3 belongs to A. However, event B has not occurred because 3 does not belong to B. So please see this distinction between events and occurrence of events. In order to talk about events, we don't need to perform the random experiment. Say, in order to write down the event that the outcome is odd, I don't really need to roll the die. If I tell that the outcome is odd, you know which event I am talking about. That is 1, 3, and 5. However, when you talk about occurrence of event, we are actually performing the experiment and observing whether the event is satisfied or not. So that's the difference between event and occurrence of event. Sure event, that means which always happens. The whole of sample space, it will always happen because no matter what the outcome is, the outcome will always belong to the sample space. That's why this is called the sure event. On the other extreme, consider the null set. This is subset of any sample space. So this is also an event on its own right. However, whenever you perform the experiment, irrespective of what the outcome is, that outcome can never belong to the null set, because the null set by definition is an empty set. That means the null set event can never occur. That's why it is called the impossible event. Now, we need to understand the basic rules of set theory, because as you have already seen, when you talk about events, inherently we are talking about sets. And as we will go on further into probability, you will see lots of applications of set theory. Of course, basic set theory, but you need to understand basic set theory in order to understand probability. So here are some basic rules of set theory. Let's go through those one by one. Let me bring the drawing facility here. Yeah. So commutative rule of union. What does it say? This one. Actually, both of them mean the same thing. They both represent the set which includes all the elements which belong to either A or B. What about this? A intersection B is equal to B intersection A. Actually, both of them indicate the set which includes the elements that are part of both A and B. So let's draw a small diagram here. Say this is A, this is B. Now A union B means all the elements which belong to either A or B. So all the dotted region. However, when you talk about intersection, by the way, A union B or B union A, as you can see, they mean the same thing. Now, when you talk about A intersection B or B intersection A, we mean this part, this shaded part, which include only elements that belong to both A as well as B. Now, this one, let's come to this one. Associative rules of union and intersection. First, let us talk about union, associative rule of union. A union B union, say A union B union C. That means first you take union of B and C, and then that result you take union with A. That will be same as if you take union of A and B first and then with C. Compare this with the algebraic result. X plus Y plus Z is same as X plus Y plus Z. That way you will remember. Say this is the result of algebra or basic rule of algebra, where X, Y, and Z are three numbers. Similarly, A intersection B intersection C, that means first you do intersection of A and B, B and C, and then that result you intersect with A. That will be same as if you do A intersection B first, and that result you intersect with C. And again, you compare with this result. Here, either union or intersection will play the role of plus. Typically, you can compare intersection with dot or multiplication. In that case, also X into Y into Z is equal to X into Y times Z. That way you can remember. Let me clear this drawing. Okay. Now comes distributive law. What is it? There are two kinds of distributive laws. First one is intersection over union. So A intersection B union C will be same as A intersection B and A intersection C taking union. This is A, this is B, A, B, and C. Let's write down some numbers to these parts so that you can identify. 2, 3. There are 8 parts altogether, and we are just numbering them so that we can easily talk about the things next. Say, when you talk about B union C, which all parts are included here? B union C. See, C, B means 2, 3, 4, 5, right? All these 4 parts are included in B. And C, in addition, has got 6 and 7. So this one and 6 and 7. So that's what is B union C. When you intersect with A, which all among these, which all parts are part of A? Only 2, 4, and 6. Only 2, 4, and 6. Right? 2 belongs here, of course. Belongs here. And 3, does 3 belong to the intersection? No, because it doesn't belong to A. So this one is ruled out. This one is taken. 4, does it belong there? It belongs to A. Yes. Does 5 belong to A? No. Does 6 belong to A? Yes. Does 7 belong to A? No. That's why when you do this, when you do A intersection B union C, you get only these parts 2, 4, and 6. Next, let us see what is the right hand side of this one. What is this part? A intersection B, which all parts are there? A intersection B means only 2 and 4. And how about A intersection C? That is A intersection C. Please observe that A intersection C gives us the parts 4 and 6. So when you take union of these two, which all parts we get? We get 2, 4, and 6. That's precisely what we had got here. So when you take this union of this, we get same as this one. That's why we got this rule. Similarly, you can argue that this also holds. How do you remember these rules? Let me clear this drawing. Okay. Let me talk about this. Say, if you treat intersection as dot and union as plus, then we know the basic rule of algebra as this: x into y plus z is equal to x into y plus x into z. Similar thing is happening here. A intersection B union C is equal to A intersection B union A intersection C. So here, dot, this rule is what? The distributive property of dot over plus. And this one is distributive property of intersection over union. However, here there is a little diversion from our rules in known algebra of numbers. Say, although this one holds good, that is x into y plus z is equal to xy plus xz, this is true. Now, what about this? X plus y dot z, is it equal to x plus y dot x plus z? The answer is no. However, in set theory, it happens. Actually, this is also true. A union, this rule also holds good. In other words, union also distributes over intersection. Next, let's come to another important rule of set theory, that's called De Morgan's rule. What is it? A union B complement. By the way, what is this notation? A complement. That means all the elements which are not in A. Say, this is the Venn diagram. This is the universal set U. Suppose this is our A. In that case, A complement means all the outside part. All the outside part is A complement. There are two more notations for the same thing. We may also write the same thing as A complement or A dash or A bar. All these three notations denote the same thing, that is A complement or the complement of the set A. Now, what does De Morgan's rule say? A union B whole complement is equal to A complement intersection B complement. Let's see. Again, let us number the regions. Region number 1, 2, 3, and 4 is outside. In that case, what is A union B? A union B means the regions 1, 2, and 3. So what is A union B complement? A union B complement will be the region only 4, right? How about this part? How about the right hand side? What is A complement? A complement, let me clear the upper part. That way, I'll make some more space. Okay, what is A complement now? A complement means the regions 3 and, by the way, this one is A and this one is B. So A complement means the outside of A, that includes the regions 3 and 4, and B complement is the region 1 and 4. So when we take intersection of A complement and B complement, which all regions will come under that? Only region 4. See, compare that with this. Compare that with this. We have already got. That's why this rule holds good. Similarly, A intersection B complement becomes A complement union B complement. These rules are also very useful and they are known as De Morgan's rule. Let's clear the drawing now and go to the next screen. It always takes a little time to go to the next screen after we draw the... Oh, sorry, I've closed the PPT. So let me bring it up once again. Yeah, here. Next, we will talk about the size of a set A. What is the size of a set? Uh, all right. Let me just talk about the size of a set. Oh, now it has come. Good. It gets stuck while shifting from one to another after using the pen tab. So anyway, it has come up now. So let me discuss this part. What is the size of a set? Size of a set A, that is denoted by this. Let me bring out this. Okay. Size of a set A, that is denoted by this symbol, denotes the number of elements in the set A. It's called the size of A. So what is the size of the null set? 5. That will be equal to 0 because there is no element in the null set. Now comes a very important formula. We will be using this thing a lot in probability theory. This is called inclusion-exclusion principle. So let's see what it is. Suppose there are two sets A and B. Say, for example, A equal to 1, 2, 3, 4, and 5. And B is equal to 2, 4, 6, and 7. What it says is, size of A union B will always be equal to size of A plus size of B minus of size of A intersection B. By the way, A intersection B, we have a shorthand for this. We denote it also by AB, and A intersection B intersection C, we will denote this by simply ABC. That way, it saves us some trouble of putting the intersection sign in between. Let's look at this rule. Inclusion-exclusion principle when there are two sets. It says that the size of the set A union B will be same as size of A plus size of B minus size of AB. Is it happening here in this particular example? I have randomly chosen an example without any thought into this. So what is size A here? This is 5. What is size B? Here it is 4. What is size A intersection B? What is the set A intersection B here? It includes only two elements, 2 and 4. So the size of A intersection B is equal to 2. And what is the set A union B? This is equal to 1, 2, 3, 4, 5, and also the elements 6 and 7. So what's the size of A union B? This is equal to 7. Now let's see whether this thing is holding or not. The left hand side is equal to 7. How about the right hand side? Right hand side is RHS equal to 5 plus 4 minus 2. So again 7. So left hand side is same as right hand side. That's what this rule tells you. There is a similar rule when there are 3 sets or 4 sets or 5 sets. Let's discuss the 3 sets one. When there are 3 sets, A, B, and C, then the rule is like this. See what is happening. In order to remember this, you understand the rhythm of this formula. Right hand side, that's the longer one. That's what you need to remember. First, all the single element symbols are coming. That is size of A plus size of B plus size of C. Then all the two symbols together, AB, BC, CA. Then the 3 symbols together, ABC. Of course, there are no 4 symbols, so it stops there. Now, when the single letter symbols are coming as size, they are all as plus. When there are symbols of 2 elements, that is AB, BC, or CA, their signs are negative. Observe this thing. Sign of AB is also negative, same as BC, same as CA. And then when you take 3 symbols together, then sign of ABC will be again plus. So alternately, the signs go from plus to minus to plus, and if there is also D, then it will be plus again. I'm not writing that down, so it's an exercise for you. Let me clear this drawing now. All right. So that brings us to the end of this session. Hope you liked it, and see you in the next session.